Hello again. Today we'll look at binomial hypothesis testing in this lecture. So the idea here is now we're taking a look at inferences. Let's go back and take a look at the motivating examples first. So first example is toss a coin 20 times and we get 13 heads. Is the coin fair or is it biased towards heads? So based on the 13 heads, we get 65% or 0.65 heads in this case. Probability of heads is 0.65, and this is quite large compared to 0.5, but is it large enough? The question here is, do we base it simply on this 13 heads out of 20 or this 0.65, or is there some other way of doing this? Another example is marketing campaign was launched to try and increase the market share for coals, which stands at 60%, actually it's more like 30%. The survey of 1,000 people at random, selected at random, found that 650 of them shopped at Coles. So is this a sign that the Coles market share has increased? So it used to be 60%, now it's 65%. Another example, Telstra's mobile share based on a survey from last summer was 40%. Another survey this summer, over 500 people at random gave us 190 saying they had a Telstra mobile, and that's 38%. So does that mean that Telstra's share has declined from last summer? An example from genetics. Mouse gene genomes have 19 non-sex chromosomes in addition to the X and Y sex chromosomes. Of course, females have 2 X's and males have an X and a Y. The total proportion of mouse genes on the X chromosome is 6.1%. Now, 25 mouse genes are involved in sperm formation. There are two theories about how these things work. One is that this is entirely by chance, and that's called the independent chance model. And the second is there's some evolutionary aspect of this. In other words, this thing doesn't happen quite at random, and there's some direction or some channeling of this. So in the mouse genes, what happens is that 10 of 25, that's 40%, are on X chromosome. This is larger than that expected by the independence model. What is this? Unusual? In other words, 10 out of 25 is 40%, more than what you'd expect. In other words, is the independence model incorrect for mice? So how does this work? Well, the way it works is that all of these 3 or 4 examples look similar. We all have, in this case, a binomial distribution, and we're looking at the probability, in this case, of success, and we're trying to determine a value for it, or compare this with some other values. The method here that we can use to determine this, to answer this question, is different for different sample sizes. For small sample sizes, there's a different method we use, and for large, another method. But what we're going to deal with here is a method that works for all sample sizes. But usually we're looking at something smaller here in the method that's used mainly by textbooks. So we'll see how it develops from here when we get to large sample cases. So the steps here are the following. First of all, let's define ourselves as an variable. So we'll work through this coin tossing example of 20 tosses of a coin, and we get 13 heads. Is the coin biased in favor of heads? So let random variable x denote the number of heads obtained in 20 tosses of a coin. Then x is binomial. The 20 is n, that's known to us. And the p here is probability of heads. That's unknown to us. So p here equals probability of a head. And this is the parameter that we're going to discuss and argue about. So inference deals with the value of parameter p in this case. And here, as we said in the box, inference always deals with population parameter of some kind. In this case, the model is binomial NP. The n is known because we fixed it in advance, and the p is unknown, and we'll take a look at the values for p. The next step is stating hypotheses. So there are 2 hypotheses that we will state. The first is the null hypothesis, and that essentially states the current belief, or the belief of no change, or the null, if you like, the default position. So in the coin tossing example, there's no reason to believe the coin is unfair. So we start off by believing the coin is fair. In other words, that means probability of heads is 0.5. The alternative hypothesis is the counterclaim. This is what is the change we're expecting to see. So we're trying to decide if the coin is unfair. If the coin is biased towards heads, that means the probability P will be bigger than 0.5. Probability of heads will be bigger than 0.5. So those are two hypotheses. The next step is, how do we decide this? Well, we don't just look at the number 13 out of 20. We actually base it on probabilities, because that makes it more objective. Otherwise, you might think 13 is not big enough. I might think it is big enough. So we take a look at the observed number of successes, in this case the observed value of our test statistic, and we find that 13. So we compute this probability of getting 13 heads, assuming the coin is fair, assuming the null hypothesis. So this P comes from the null hypothesis value. Because obviously to compute the probability I require some value for P, and we pick it from the null hypothesis value. So problem is, 13 is what we observed, P is the value from the null hypothesis. Question will be, is this probability large or small? And that's something we have to decide. In other words, are we likely to get 13 heads from a fair coin? And if you think that 13 heads are too many from a fair coin, then anything more than 13 is also too many. So the p-value is actually probability of extreme values compared to our null hypothesis. So if I am getting 13 or more, that's extreme compared to, say, if p is 0.5, I expect 10. So it's always going to be away from that. So 13 or more, even p is 0.5. Now, if I look at binomial tables, I'll work out probability of less than equal to 12 and subtract it from 1. So probability of x bigger than equal to 13 is 1 minus probability x less than equal to 12 for probability p 0.5. So I can find that in binomial tables. So here are my binomial tables. We haven't done this before. So there are two parts of the table over here. The first is individual probabilities, and this lists probabilities for various values of n and various values of p over here in the table. And so if I go back to my lecture note and I take a look at this probability of getting 13 heads, if p is 0.5, so I go back here, take a look at 20 to start off with. N is 20, so this is over here somewhere, and 0.5 is in the middle over here, and I'm looking at 13 heads, and that must be 0.0739. So that's my 0.0739. But I'm now looking for x less than equal to 12. So in my binomial distribution, I go further down and I look at cumulative probabilities, probabilities of being less than equal to. So it says here, the table entry is x less than equal to k, where x is binomial. Here my values for k over here, and there's my n's down this way, and my p's are across over here. So again, I go to 20, n equals 20, and p is 0.5 is down the middle here, and I want 12 or less. That's over here, 0.8684. So it's 1 minus 0.8684, and that gives me 0.1316. So the decision is based on this p-value. If the p-value is small, then we'll say the data and the null hypothesis are inconsistent. So one of two things happens. Either the coin is not fair, that means that is biased in favor of heads, or a rare event has occurred. So I can get 20 heads out of 20 tosses of a coin. It won't be very often, it's not very likely, but I can get it. So rare events in hypothesis testing are ignored. We say that these things don't happen. And so we conclude the coin is biased in favor of heads if the p-value is considered to be small. The question is, what is small? And so here we get this idea of a significance level. So we define or determine a significance level in advance, which essentially says that if the p-value is bigger than significance level, there's no problem. So small or large is in relation to the significance level. Usually 5% is what is set, or 0.05 as the benchmark. Anything lower than that is too small, bigger than that's big. So in this case, my p-value is 0.1316 and is bigger than my significance level 0.05. So we conclude that since p-value is bigger than 0.05, there's insufficient evidence to reject the null hypothesis at the 5% level of significance. So here we'll conclude there is no evidence that the coin is biased. In other words, I can get 13 heads out of 20 tossers quite often, and so the coin is unbiased. Some points about writing conclusions to hypothesis tests. The first thing is it must be written in simple terms and in terms of the question of interest. So it must answer the question, be unambiguous, be impossible to misinterpret, and it must be in the language of the context of discipline. So don't simply say things like, we failed to reject null hypothesis or we reject null hypothesis. We actually form it back in terms of the question and the discipline. And let's look at one more example here. A garden center claims that only 10% of their mango seeds fail to germinate. So a mango farm trials 20 of these seeds and they find 4 of them don't germinate. So 4 out of 20 is actually 20%. That's double the 10%. The question is then, is the claim overstated? In other words, the percentage that actually don't grow is more than 50%. So we start again by defining ourselves a random variable of interest. So x denotes the number of seeds that don't germinate out of 20. And so this is our test statistic. This is what we'll use to test the hypothesis or this claim. So this random variable x then has a binomial distribution. The 20 is known to us and the p is unknown. The p here is probability a seed we're looking at don't germinate, so does not germinate. So what will my null hypothesis be? Well, the null hypothesis will be essentially the claim as it stands. So it'll be p equals 0.10%. And the alternative is the counterclaim. So here, essentially, the idea is that if more than 10% don't germinate, then the claim doesn't hold. So we need to look at which way it goes. So here, of course, it will be bigger than or less than, but bigger than is what we're looking for. Sorry. We're looking at p bigger than 0.1 or 10% as what will be counter to the claim of the garden center. Observed value here is 4. We found that 4 did not germinate. So the p-value of the test here is p-value equals probability that x is. Now you'll notice here this is bigger than there. So this also will be exactly in the same way, bigger than 4, given that p is my null hypothesis value of 0.1. So there are a few things you'll notice here. I could have said less than 10% here, because of course if anything less than 10% doesn't germinate, that's still okay for the company. But this is always the equals value, that's enough. And this is never the equal. So equals is never in the alternative. Equals always, and this is going to be bigger than or less than in most contexts. So here x bigger than equal to 4. I had 4 observations. given p is 0.1, and so that's 1 minus probability x is less than equal to 3, given p is 0.1. So I'm looking again at my binomial distribution as before. I'm looking at 20, 0.1 this time. So 20, this is the 0.1 column, and I'm looking at x less than equal to 3. That's 0.8670. Let me just check that. This 0.1, cumulative, 20, less than equal to 3, 0.8670. So it's 1 minus, what happened there? So that will be 0.1330, which is bigger than my significance level of 0.05. So here we would conclude well, before that we will say there is not enough evidence to reject the H-naught. So let me say there is insufficient evidence So we'll conclude here based on the data and the analysis we've done here, based on this analysis, so we haven't rejected the null hypothesis here. So there's nothing wrong with the guidance and this claim. And so right, there is no evidence. Oops, this is playing up with the funded, sorry. Against the guidance and this claim. So if we did not perform a hypothesis test in this case, and simply looked at the numbers, 4 out of 20 not germinating, we would say there's 20%, and so we would say the market center's claim is not correct. But because we're taking a look at this as a random phenomena, so 10%, if on average 10% don't germinate, most 10% don't germinate, then in any single trial of 20, you can get 4 not germinating, and that's not against the claim, that's not against the claim by the company because of the random nature of these things. So essentially all we've done over here is modeled the randomness and based our decision on probabilities. So here's the example of the mice we saw earlier, and I'll let you try that yourself. I've set this up to start off with. So we're looking here at 10 out of 25 of the genes were on this chromosome, and we were asking the question, is this larger than expected by the chance model, independent chance model? So we set the whole thing up as y is the number of genes out of 25 on the X chromosome, then y is binomial, 25p, we've got 25 genes, and here P denotes the proportion of genes on the X chromosome. So hypotheses of interest here are going to be, and you can formulate that yourself and see what you get. Because as it says earlier here, the total proportion is 6.1%, and so what we're getting is much more than that. In other words, we will take a look at this independent chance model compared to the other evolutionary model. That's all for this. Thank you. Bye.